Hello friends, this video on Chemical Kinetics part 25 is brought to you by examfear.com. No more fear from exam. So let's see the next theory, which is the collision theory, which is there to explain the same experimental data, that is when you increase the temperature, the reaction rate increase in a different way. So as per collision theory, a reaction will happen if two molecules collide with a speed like a car. There has to be a bang. If they are slow, the reaction won't happen. There will be ouch, but there won't be any reaction. Also, even if they are at very high speed, there has to be proper orientation. For example, in this case, these two cars are trying to hit back to back, right? Even if the speed is high, they are safe. So the point we are trying to drive here is speed of molecule is important, right? Because in these two reactions, this doesn't have speed, so reaction didn't happen. Here the bang happened, the product would form. Also with speed, if you see, the orientation also matters. If you see the orientation, right? The orientation and the angle at which they are reacting. So they came up with this concept of orientation also. Orientation of collision. And this theory is called collision theory, where they're saying that the collision, for a collision, effective collision to happen, the speed of the molecule is important and the angle at which they are hitting is also important. Correct? So if you see the theory of chemical reaction, it says that also if you increase the concentration, the number of molecules increase, so the number of collision will also increase. And they are saying that collision is nothing but reaction. Right? You see, two molecules, they collide and they form product. The orientation was proper. Two molecules again, they collide, but the orientation was not proper, they just bounce back. No product. So if you see once again, two molecules, they collide with a good speed, proper orientation, they bang and the product was formed. Two molecules with the same speed collided, but angle was not proper, they just bounce back. Right? So if you see, though the Arrhenius equation we have discussed is applicable for a wide range of circumstances, this collision theory was developed independently actually by Max Tronst in 1916 and by Lewis in 1918. The gap of 2 years, and they developed independently, and that's why we say the collision theory was developed from 1916 to 1918. Actually, it was developed independently by two different people in the span of 2 years. It provides a better insight into energetic and mechanistic aspect of the reaction, and it is totally based on the kinetic theory of gases. So in this theory, what happens is the molecules are supposed to react if they collide with the relative kinetic energy along the line of center. If you see, yes, they collide along the line of center, the product is formed. If they collide, they don't collide along the line of center, they just bounce back. Right? So collision has to be good with a good kinetic energy, right? That is kinetic energy greater than activation energy, and it has to be along the line of center. This expression is almost similar to the Arrhenius equation. We'll see that. And it says that when two suitable particles or the reactant they hit, only certain percentage of the collision lead to significant chemical reaction. Only some percentage leads to significant chemical reaction, and this is successful reaction or successful collision is called successful collision. So if you see here, this is an example of successful collision and this is an example of unsuccessful collision. Right? Both the collision will have kinetic energy greater than activation energy, but only certain percentage will actually form product. So in case of Arrhenius, he never talked about the percentage of successful collision or percentage of non-successful collision. Here they've implemented this parameter of successful collision. They are saying that not every collision leads to a chemical reaction, only a fraction or some of these collisions leads to a chemical reaction, and these collisions that lead to chemical reaction is called successful collision. Correct? So if you increase the concentration, here we have low concentration, here we have more concentration. So you increase the concentration, what happens is, or you increase the concentration or temperature also, you have more collision, and more collision means more successful collision, right? So you increase concentration or you increase temperature. In both cases, this implies more collision. More collision implies more successful collision. And this implies more reaction or faster reaction. And that is the logic they have given. They're saying you increase the concentration, then also you'll have more collision because more molecules to collide. Increase the temperature, then also you'll have more collision because these molecules will have more kinetic energy and they'll collide all the more with the higher frequency. More collision implies more successful collision because a certain percentage of the collision becomes successful collision. More successful collision implies faster reaction. Also, they told that the role of catalyst also is explained better using collision theory than using Arrhenius theory. So they are saying this collision, if you have collision here, more collision, but if you use a catalyst, then more conversion to successful collision. So what I'm saying is, if there's a reaction here, for every 10 collision, only 2 are successful without catalyst. Without catalyst. For every 10 collision, I have only 2 successful collision. That means proper orientation, proper speed. But if with catalyst, it can happen that for every 10 collision, 8 are successful. It can happen. We'll see that why it happens, right? So that explains the role of catalyst all the more, because it is seen that with catalyst the rate of reaction has increased. So Arrhenius equation was not able to explain that concept properly, why the catalyst is playing such a major role, but this collision theory is able to explain that role properly. And they gave their own formula. The rate is nothing but Zp e to the power minus Pa by Rt. This part is same. This is nothing but the molecules that take part in reaction. Here the probability thing they have added. Probability, why they have added? Because they are saying that not every collision is a successful collision, right? Only some of the collision becomes successful collision. So that probability thing they have added, that is called probability of collision or steric factor. And this Z they have added is called nothing but collision frequency. Collision frequency. And this is a constant value for a given reaction. It depends on the state of the reaction, where the reaction is happening in solid state, liquid state, and property of the reactants. Right? So here they are also stressing on the proper orientation of the reactant molecules. So proper orientation with a decent speed, that is kinetic energy greater than EA, they'll form the product, but decent speed but no proper orientation, no product is formed. Right? So in this collision theory, both activation energy and the proper orientation determines the rate of reaction. Let's take one example where the collision theory explains why the proper orientation is mandatory. So we talk about the formation of methanol from bromoethane. Right? So I have bromoethane. I have to form methanol. This OH minus will attack. Now if you see, if you must have seen the organic chemistry, this OH minus has to attack from backside, because bromine is electronegative, slightly negative charge, carbon is slightly positive charge. So this carbon is prone to attack, and the attack has to be from backside only. Right? If it attacks from front side, the reaction won't happen. The attack has to be from backside only, and thus if you see, the orientation comes into picture. Right? So if the OH minus attack at this position, there won't be any reaction. If OH minus attacks this hydrogen, no reaction. It has to attack this carbon and also from the back only. If it attacks from this side, then also no reaction, because there won't be much space. It has to attack from this side only. So with this, we have seen this kind of reaction. It will form an intermediate, that is OH, C, this is H, this is H, and this is Br. Right? This is an intermediate it will form. This is a complex intermediate. And then Br minus will leave, is a good leaving group, and then OH will take its position. Right? And Br minus will leave. and there will be a negative sign here somewhere here. So this is a good example to show that the orientation also plays a critical role in the reaction. Thank you. Visit examfear.com to watch more videos, attempt free online tests, get free study materials, find tutors and mentors, and much more. Thanks once again.